Suppose that a stream of fluid flows steadily through a horizontal pipe of varying cross-sectional diameter. Neglecting viscosity, where is the fluid pressure the greatest? So let's draw a hypothetical situation. Let's say we have a pipe, or a blood vessel for that matter, where in one area it has like a larger cross-sectional diameter, and then here it has a narrower cross-sectional diameter, right? So if we think about it, there's going to be fluid flowing here with a certain velocity v1 through this cross-sectional area a1, and then it's going to be flowing here with a v2 with this cross-sectional area a2. Now, if we apply the continuity principle, which states that v1a1 is equal to v2a2, right? So this actually is saying that the volumetric flow rate has to stay the same. If a1 is greater than a2, the only way that these two sides could be the same is if v1 is less than v2. So v1 is less than v2, which means that the fluid is actually flowing slower in the greater cross-sectional diameter or area, cross-sectional area location. Okay, and it's flowing faster here. Now, what consequence does this have on fluid pressure? And when we talk about fluid pressure, by the way, we mean the pressure that the fluid is exerting on the walls of the container. Okay. Well, to explain this better, we should take a look at another principle/equation, which is the Bernoulli principle, right? And the Bernoulli principle, if we write it mathematically, is basically saying that the pressure at point 1 plus the kinetic energy of the fluid at point 1 with a velocity v1 plus the potential energy of the fluid essentially at height 1 is constant, I'm going to say, okay? So it's equal to the same thing, but at, like, say, a different height, a different pressure, a different velocity. Now here, we can assume that the height is basically the same on both sides, right? So this is not going to factor in. So all the energy is basically in pressure, okay, plus the kinetic energy. So we can actually say that P1 plus 1/2 the density V1 squared is equal to P2, the pressure at point 2, let's say here, plus 1/2 the density V2 squared. So what can we say? It's kind of like the continuity equation in that both sides have to be constant, right? And we know that V1, the kinetic energy, must be lower than here, right? Because the velocity 2 is greater than velocity 1. So this is kinetic energy terms. There is less kinetic energy here than there is here, right? And so the only way that these two sides could equal out is if the pressure at point 2 is less than the pressure at point 1, okay? So the pressure, okay, is actually going to be greatest at the point with the maximum diameter, okay? It's going to be B. And you can actually think about this as sort of, or you can think about pressure as being a sort of energy reservoir, where whenever fluid starts to move faster, so it has more kinetic energy, more energy of motion, it actually reduces the amount of pressure that it's putting on the walls of the container, and vice versa. When it's flowing slower, it basically has more time effectively to interact with the walls of the container and exerts more pressure, all right? So at the point of maximum diameter, that's going to be the time when, or the point when the fluid flows the slowest, has the least kinetic energy, and therefore is going to exert the highest pressure. So B is the right answer.